name is Pfeiffer from the Embedded Systems Academy. We offer various products and services around CANopen. For details, see our webpage. And now let's start looking into security in CAN networks. And I'm happy to say that I didn't have to put this presentation together alone. I had a little bit of help from our team here. So Chris also helped with it. And also we are working together with the Hochschule Offenburg, the University of Offenburg, and the team around Professor Axel Sikora, to bring you, well, a new security implementation for CAN and CANopen later this year. I'll tell you more about this in a few slides here. The agenda for my part of the presentation is that I want to briefly review some of the requirements that we currently see evolving from various EU regulations coming towards us. Then I'll also look at standardizations of security, specifically at the IEC 62443, and also review some of the attack vectors, security solutions available already today or already since several years. And as I said, the thing we are working on, we have the project name here, the Interlayer Multi-Participant Security. So with that, let's continue and look into the requirements for regulations first. Well, for a long time, we tried to get along here without regulations and ask for common sense. However, if you followed a little bit the news on what is hackable all around CAN and CAN-based systems, then the common sense solution really didn't work out. Simply put, CAN is just too easy to hack because, well, the downside of a standard is that you immediately know what you have to transmit to where to trigger a certain action. The better a system is documented and standardized, the more easy it is to manipulate or start injections. And some of the latest hacks go as far as that even modern cars are easily hackable by removing the headlights, putting something on the wires of the headlights, and by injecting the right order of right messages, you can not only open the car, you can also drive it away. There have been several publications around how these systems work. So the upcoming regulations that many of our customers should be worried, well, I'm not sure if worried is the right word. Well, you just have to follow them. It's no longer a voluntary or common sense thing to employ security. The first one I want to mention here is the machinery regulation. This covers all machines, and the definition of machines is quite simple. It's simply as soon as you have a drive that is not just rotating, but moves something, so there's something attached to the drive and it starts moving, then you have a machine. And the regulation does not only cover the machine builders, but it also covers partial or subsystems. So as soon as you're a supplier to such a machine, this already applies to you. And similar as we have to see with the definition of functional safety, it simply requires the protection of persons, domestic animals, property, and environment. So you shall do no harm. That's roughly what the regulation says. And for networks, it specifically says it needs to be protected against accidental or intentional corruption. And intentional corruption means that somebody is doing something to the network that they should not do. And this can be as much as user error, but well, no, intentional really means somebody wants to do something bad to the system. Interestingly, when it comes to the details, the machinery regulation doesn't specify anything. It simply refers to the EU Cybersecurity Act. And the EU Cybersecurity Act, well, the latest version is not even yet enacted. This intention is more for the critical infrastructure, but also important sectors like they define it as emerging technologies. So everything around Internet of Things, again, covers all of the suppliers. And here it simply says it doesn't matter anymore if you have here immediate harm, but you have to protect your system against cybersecurity attacks. Also, you have to really do some proper software version integrity management, and you must be able to do secure updates, because if there is something detected during the lifetime of your system that there is a cybersecurity risk with it, you need to be able to deploy and install security updates. So just with those two, I would say already 50% of my customers are directly covered by these, because although the Cybersecurity Act does not define anything about the machines, but machine regulation says specifically it applies to, should use the things from the Cybersecurity Act, automatically all machines fit in here too. And this is not really the end of it. There's another one under discussion, the Cyber Resilience Act and Resilience Act. And that then simply becomes interesting because it defines all simply a digital system. So as soon as you have anything digital, you have to start protecting it from cyber security attacks. So putting all of this together really means what Uwe also said, it's not enough to secure your networks. Safety is also an issue here. And now we really have to find a way to do the merge between safety and security and bring it all together. Now, if we look out there, what standards can we look at when it comes to security? Then really, I only have one slide here on IEC 62443. Well, there are books and multiple hour presentations on this. So this is really just more of a link and reference showing you where to look for details. In short, this applies to any industrial automation and control system. And it's defining the entire security, putting it on 3 pillars. And the 3 pillars being that it's always the security, a combination of technology, but also procedures and users. And what when we talk about safety and security in Can Open, we typically only talk about the technology. But as Uwe referred to, there's so much more than just what we do. There's all the other things around it. And so you also have to look at all your cyber security procedures in place, the users, how are they authenticated and authorized to use certain things in the system and so on. Now, interestingly, also here we have multiple levels defined. So we have different security levels, and the wording is such that there is some room for interpretation, and they really nail it down on, well, how much effort do you have to put into something? And so the lowest level really says, well, you need to protect your system from casual or coincidental violation. So this is like maybe somebody just made a mistake or pressed the wrong button, something like this. And then coming up to the next levels, it quickly introduces intentional violation. So all other levels are that somebody intentionally wants to do something with the system. And then it just comes together with the means. So sophisticated means with extended resources is really the highest level. And this is typically like having a state actor. So really a team of maybe tens or hundreds of engineers trying to figure out how to bring a system down. So this is really the highest security level, and everything is somewhere in between. I think for us quite important is and easy to understand is that the IEC document really refers a lot to network segmentation and access control. So they want to heavily introduce network separation in zones. So where in the past we would have gateways and bridges allowing you to access everything, now you have to look at every situation where one network meets the other. If it's a bridge, gateway, or whatever, you always have to look at it as a firewall, as a sort of protection. You cannot just open it up wildly and offer full access. So if we look into the traditional method here of the automation pyramid, then we can see that CAN-FD is typically here somewhere in the lower layers. And wherever you interface with any of the other layers and other networks, always imagine a little firewall here where you have to carefully select which data you want to make accessible across borders. Please note that if in an industrial environment, we could still also say this doesn't need to be all fixed assets. This could also be movable assets. So if this is a forklift or other thing moving around, this could be, yeah, a moving mobile system also. Now, let's look at some of the attack vectors that we have seen implemented by various attacks in the past. I would like to differentiate a little bit here between data in motion and data in rest, really not worrying too much about all the many side channel attacks there are, because they are not really of concern of us on the can open level. What we are mainly concerned with is the traditional network sniffing, or as soon as someone has access to our CAN wires, what can that attacker do? So they can do sniffing, replaying some messages, inject messages, or if they knock out one of the other devices, they can try to do imposing, being an imposter and trying to behave like that device. So this is really the main thing we are concerned with. But also, if we, as Uwe said, look at the big picture, always keep in mind, this is just a little puzzle piece. If there is an option via this network to do access a bootloader, then of course code could be imported into one of these devices this way. However, if you look at today's modern microcontrollers, the bootloaders typically have 3, 4, 5, or even more different communication methods and options on how to load code in here. So these I would all put on side channels attack and say, well, yeah, in the total system, you need to take care of it. But on the CAN open side or CAN side, we only check maybe the bootloader that is CAN activated. We can't control any of the other bootloaders out there. And also keep in mind, as soon as any of your devices has an exchangeable memory card, if it's USB, SD card, or has any remote access or an interface to another network, then this is always a point of security attack possibilities. But as I said, is not really in scope of when we want to protect just the CAN and CAN open communication. Again, this shows that the security and the safety we work on is really just a small puzzle piece. You, in the end, you have to look at the big picture. So when we are looking at threats, we also have to ask ourselves, where do they originate from them? Who is the bad actor here? And this can be trying an unauthorized user to take over a system, stealing something, maybe just trying to steal the intellectual property by re-engineering something, or introducing something with which you could do a ransomware attack. And from a security perspective, the most challenging situation is always when the legitimate user or owner is the threat, because the legitimate user or owner maybe wants to operate the system outside the safety margins. You could imagine that for profit, you can try to overload certain transportation systems, and suddenly the legitimate user or owner is your possible attacker, trying to manipulate the system so that you can overload it or operate it a crane higher, wider than safe. Now, if we look at the other challenges that come with CAN, we already talked about the limited data size and frame sizes. But also, I wouldn't want to underestimate that there are still a lot of lightweight microcontrollers where we couldn't deploy the same security mechanisms that we run on web servers and internet security. So there will be always some downscaling because of the performance available in these small embedded microcontrollers. The potential security measures that we can take, of course, is trying to authenticate the communication or encrypt the communication as needed. And there will be several challenges. That's the key management, because for any type of cryptographic security, we need keys. And the biggest question really then comes down to what's the best and easiest and securest method to introduce these keys in the first place. And as I said earlier, well, even these keys used may not always be available to the legitimate user or owner if we think these could be the bad guys. And not all of these challenges can be really solved on the CAN level, because there's no concept for different users, and also the key management would really require some other level, working level. When it comes to CAN, then really one of the important things is that the security needs to be a combination of methods. There's not a single solution that will cover all our security needs. We always, again, have to look at the bigger picture and do a combination of multiple things. And the big two groups that I would like to show here is that there are non-cryptographic methods, and they are obviously the cryptographic methods coming in a little while here. And the non-cryptographic methods are as simple as maybe having physical access limitation. If your CAN network is deeply embedded in a computer tomograph, which is a big machinery standing somewhere in a hospital with very strictly limited access, and all the CAN wiring is deep inside the machine and cannot easily be opened, well, then you could probably discuss on how much additional cryptographic method do you require. And on CAN, there's one simple method that also doesn't require any cryptographic methods, and this is the ID guarding or the injection detection. And the basic idea is, because every node on a CAN system can receive everything, when there is a CAN ID injected, that is not authorized, somebody will or has the option to recognize it. So if I'm a sensor, I'm regularly producing a CAN ID 180. So and I now receive a CAN ID 180, then I know somebody else injected the message that, or the CAN frame that belongs to me, and I can now try to implement countermeasures to that. So really, this is a very effective low-level detection method of if somebody is trying to mess with your system. Of course, there are up and downsides. I'll evaluate them in a while here. Now, when it comes to cryptographic method, then everything what I've seen so far is really based on pre-shared keys. So there are symmetric keys that need to be shared before we start, typically at some point at the system integration, when the entire system is switched on for the first time. And because we want to protect the pre-shared key, there needs to be some derivation method where keys are derived from this key to limit its exposure. And of course, the cryptographic methods chosen have to be suitable for lightweight microcontrollers. And this would then allow us to do things like having a secure authenticated heartbeat, and also authenticate and encrypt frames. Let's have a closer look at the CAN ID guarding. What can we achieve with that? So it really offers a spoofing and tamper protection, because if all nodes on a network monitor the system for all injections, and each node knows the CAN IDs that it uses for transmission itself, then with such a method, we could completely protect a system. And there's actually even a hardware solution for this available since, I think, already 5 years or something like this. There's a specific NXP transceiver that, if introduced here to the system and probably configured, will simply not allow illegal CAN IDs to pass. And so really, you could say this ID guard is already like a firewall. It does not allow IDs to go past if they are of the wrong ID, or if a wrong ID is inserted here. What this transceiver will do, it will actually kill it with an error frame. So an ID that is illegitimate will be destroyed. That is the hardware solution. When there's a system with bridges and repeaters, then of course this is always just local. So these ID guards only work in a local domain. Of course, this can also be implemented in software, with the only downside being this with using regular CAN controllers, a node will not be able to destroy a message and kill it, but it will be able to recognize it, and we can then implement some mechanism to see what do we do with this information if we detect such an injection. Then, of course, what can be done is in the next level up is a CAN cryptographic layer. So the CAN cryptographic layer means that we have these pre-shared keys, and depending on the security method, there will be some authentication, some encryption, and these security layers share a common key, and we have the security cryptographic layer built into those devices that participate. And this can typically, depending on configuration, work system-wide, even if there are multiple domains. There are a few things to consider, but in general, this is possible. One such commercial solution is, for example, CanCrypt, which is available since 4 years now. However, this is limited to a maximum of 16 participants. So a maximum of 16 nodes could be sharing here a secure communication. And the third option I would like to show is something called DTLS. It's a variation of the transport layer security known from the internet. They created a scaled down version, which is called the datagram TLS. And so it's a little smaller in the amount of data required. However, we are still talking several hundreds of bytes for the initial authentication. The main reason I'm mentioning it is not so much for communication within a CAN or CAN open network, but from all the things we discussed here in the security, the nice thing about DTLS is that now you would allow the option to cross networks. So a DTLS connection could be made also out of the CAN network. And so we could have, for instance, some external charger or some wire cloud remote access and really build a point-to-point security feature here. So these are 3 different methods, and we already introduced these 3 and compared them in a paper 4 years ago. And this slide is more for your reference, giving you a little bit an idea what the main difference between these 3 methods is, what type of protection they provide. Also, the interesting here, the relationship, the DTLS is a pure one-to-one, and many of the other security solutions even currently worked on, like in CAN-XL security, is a one-to-one, meaning really you need one individual security channel for each secure communication that you want to establish. Whereas with the ID guarding and the CAN security layer, it's always a secure grouping that you try to achieve, where multiple devices come together in a group. I'll cut this a little short. It's in the slide here for your reference. So besides these 3 methods we already had, other solutions available are, well, there are by now 6, 7, 8 various scientific papers that offer individual application-specific solutions to how to do CAN security. I've not seen them as an off-the-shelf solution. AutoSAR has also, for the automotive industry, tried to standardize a little bit the communication, the secure communication. This has still many manufacturer-specific components and is also channel-oriented. And with CAN-XL, we already said this is still under development. The security feature is still under development to be built in. However, there is still quite a bit of work ahead of them. And as I said, it's a one-to-one security. Now allow me to briefly introduce what we are currently working on. So this is a project funded by, thank you to all taxpayers here in Germany. So this project is partially funded by a federal ministry, and it allows us, together with the University of Offenburg, to really now put in more thought and more test time in adding security. And our primary goal is to in a first goal, to have CAN open security, but the secondary goal is really security for all small packet networks. So it could also be adapted to Modbus, maybe even LIN, who knows, we'll see. The basic idea here is that we have a trusted group security. We want to have the assurance that communication comes from within the group. So it's not a one-to-one, but it's a many-to-many. We also will introduce some basic functions to help with the key management, to derive and distribute keys, how keys are rolled, rolling keys. We'll implement also different security levels to somehow fit within the other standards. And what we really want to achieve is we want to be able to protect all communication, not just individual channels. Because one thing that comes up with the Cyber Resilience Act is they really define everything digital needs to have some cybersecurity. So I wonder if at some point it's not enough to have single selected secure channels. Maybe we really need this security for everything. And of course, we want to have unlimited uptime, meaning all the householding has to be done while running. So if keys are changed and derived, this needs to be done without any interruption of the system. The prerequisites that we need for this ILSEC layer is that when we use classical CAN, we still rely also on the injection detection, because due to the limited payload, the authentication tags used will be of a bit size that under regular scrutiny would not pass. But in combination with all the other features that CAN already has, they are, at least what we believe by now, in an acceptable level. Again, we also have pre-shared keys, and we will reference to another work done by the University of Offenburg, Field PKI, Public Key Infrastructure for Field Bus Communication. For now, this is just the reference, so I'll keep it in here. And we have already seen that the transport layer security was scaled down a little bit. Well, we can scale it down further. Our working title here is the micro TLS, and it's using pre-shared keys. And the nice thing here is that we can now really scale it down to a point where it's usable within CAN or CAN-FD communication. And also we need some date and time synchronization, but this has been solved already in CAN Open in the past. With this slide, I just want to briefly show you why we call it interlayer security, because it really sits in between the layers. And the idea is to have it so transparent that you have no direct function calls into this layer. So really, it should go right within a communication layer, and all communications also to within this layer go through your regular channels. And the idea here is that we define an internal control plane. So literally that some sort of security task that you have on your application layer can use, in this case, CAN messages to communicate with the internal control plane. And that there's an external control plane where also some CAN IDs are reserved for security, directly handled from within this layer. And then on the data plane, you can really look at the data plane implementation here in the middle, again, as some sort of firewall. It will only let those messages pass that are secure. So up here in your data task in the application, you will not receive data that is unsecure. You only will receive secure data. So I'm now running a little out of time. I'll cut this a little short. This is the shortened micro TLS implementation. And really it comes down that a security level known from TLS can be adopted onto CAN by just exchanging a total of 4 frames. So you have initially 2 frames exchanged with basically random data and some householding information. From these 2 random values and the pre-shared keys, we generate a key. This is a key derivation. So at this point, these 2 have the same key if they have the same pre-shared key. And to verify if this all works, the client will just send an authentication tag. Now the servers can verify this authentication tag, and if it's okay, it generates its own authentication tag that does not only cover the initial hellos, but also this response. And at this point, the session is confirmed and open with a derived key. And this can really be done very fast. So this will be nice to see. So far, we have not yet implemented it. It's only a specification at this point. Another basic element is the secure heartbeat. You can say that in the very most simplistic implementation, we do the ID guarding combined with a secure heartbeat to offer group authentication with post-event assurance. Now, what this means is if we have ID guarding in software, it still means that an attacker could take us offline. So we want to guard an ID and want to report, oh, we just detected that somebody is trying to impose like us. And if the attacker took you offline, then you cannot communicate this with the others. And therefore, we need this secure heartbeat. Well, if the attacker takes a device offline and kills it, then it will run into the heartbeat timeout. It will stop producing the secure heartbeat. And we can see that for quite a few applications, such a low level with a delay is acceptable. However, when we really talk about safety, then really we need something like group authentication with instant event assurance, where we say, yep, every communication needs some sort of authentication tag. And here, when we are in CAN-FD or CAN-OpenFD, then of course this is much more easier because we have a field of 64 bytes, and in putting some authentication tag into the data field is easier. With CAN and CAN-Open in classical, this is much more challenging. One of the solutions we are working on with CAN-Open is to use the 29-bit CAN ID, which CAN-Open does not use at all. And this gives us 18 bits extra that we can use for an authentication tag. And we are currently examining what kind of security level in combination with the ID guarding that would give us. And in the end, the third level would be group security versus authentication, where you also add encryption. So now coming to the end and the outlook. So I've shown a little bit that there are requirements coming from regulations that require both safety and security. We have a CiA working group on this and are open for newcomers there. So same as Uwe said, yeah, please join if this is of interest for you. And so when it comes to adding security to the existing SSDO, well, Uwe already showed the frames. Well, the only thing I can think of is either we introduce yet a third frame that adds the authentication tag and security information, or another option could also here be to expand the existing CAN IDs to 29-bit. And because we have 2 of them, this would give us 2 times 18 bits, so 36 more bits. And that's already quite a bit. So that could be something. But these are just the very first initial ideas. So we have to wait and see what comes up out of that group. And with that, I would like to say thank you. And I'm now open for your questions.